Do you want to keep your secrets safe and protected by laws of nature? Hop in. Okay, welcome to the Quantum Gatsec screencast. Today we will be continuing our discussion of the BB84 protocol. We ended, there will be a card somewhere to the previous video. We ended our conversation at a moment in which we have perfect noise-free channel. And as you can see, both Alice and Bob have their messages the same. Uh, During this screencast, we will introduce Eavesdropping Eve that will try to take the messages coming from Alice and listen to it and then send it further to Bob. We will understand why it is impossible. Also, in the description, there is a link to the notebook that contains a little bit more context. And yeah, like, subscribe, share with your friend. If you want to save the world using quantum computing, we need more people. Okay, let's get to it. So we have now Alice and Bob sharing a string that matches precisely. And right now, our circuit that we've built do not have any concept of an adversary. So anyone that tries to add some noise or maybe listen to the message in general, a bad actor in our scenario. And first, let's define what attacks we are concerned with BB84, because our eavesdropping Eve has multiple ways of attacking. But in the case of BB84 protocol, we assume that Eve cannot impersonate either Alice or Bob. So maybe she can eavesdrop, but she cannot send a message to Bob saying that she is Alice, or she cannot send a message to Alice saying that she is Bob. And this is only when we are talking about the communication via the classical channel. She can mingle when Alice is sending qubits to Bob. And what Eve effectively can do is try to eavesdrop. But as we will show very soon, we cannot simply copy qubits as we can copy bits without affecting their state. So well, in theory and in practice, whenever we measure a qubit, we only get 0 and 1, and we lose the information about what was the distribution of the qubit. If you recall, for example, after applying H-gate, we have 50% chance of observing 1 or measuring 1 and 50% of measuring 0. So after we measure it, we do not know what the distribution was there. We would need to probably measure multiple times, but after single measurement, all the probability collapse to a single observed value. So how we will mirror or rather implement the eavesdropping. So we will intercept a quantum message that goes from Alice to Bob. Then Eve will act as a Bob basically, and then prepare quantum state again and send the message to Bob. Okay, and we will see that it will introduce discrepancies, but we will also see how we could protect ourselves from such discrepancies. So let's start. I could probably refactor all of this, but we will not do this. We will basically carry on. Because we are not actually implementing the BB84 protocol that will be used as a library. We are just showing the principles. Okay, so introducing Eve. we'll have this big print to basically easily see in which part we are, maybe. Okay, so let's build Alice quantum channel. Great. Alice qubits. As you recall, we can use the named qubit with range of string length that we selected in the previous video. We will give the prefixes of AQ underscore, and we will simply prepare the quantum message as we did before. If Alice A at index is equal to, but we need not to use Alice A, but Alice, no, we use Alice A, the string once again, sorry for that. Alice qubits at index, and if Alice B is 1, we have Alice quantum channel append Cirq H here, Alice qubits at index. Great. So now instead of sending the message directly to Bob, the Eve intercepts it. So Eve, Eve B, we generate the string for our guess decode procedure of particular length. And yeah, as you recall, string length, if Eve B is 1, then we apply the H gate. Hoping to decode the message properly. Here we can measure the Alice qubits with the key of Eve measurement. Okay. And now we will have Eve simulation result because she wants to actually read the message. And her guess decode is simulation results measurements with the key that is same as this one. Okay, so Eve has her guess decoded message, and now she will send the data further to Bob because she can mingle in the quantum channel. She cannot impersonate in the classical channel. So now Eve creates sneaky message. Well, or rather, she creates message sneakily. Oh, but that's the word. So Eve quantum channel Eve qubits and those will have EQ prefix and yeah, now we can do exactly the same thing as in here. But we will use Eve guess decode and Eve B, and of course the quantum channel needs to be ifs. The same go with the qubits. Great, and now Bob takes the measurements. So he basically performs this procedure. But we have Bob B generated beforehand, Bob, and what he will do is to append to Eve quantum channel, and it will be Bob measuring, and it will be Bob simulation result, and it will be Bob guess decode. And as you might recall, Bob will tell Alice that, hey Alice, I received and measured the state you've sent me. That's great. So now let's see how those messages looks like and how similar or different they are. Okay, fingers crossed, the semi-live coding. Yeah, so as you can see, introducing if Alice, hey Alice, I received measured state you've sent me. There are the B strings, and as you can see, Alice sent this string, Bob received this string, and if saw this string. So nobody has a perfect information, but what is important is that because now if we test it as we did before, we will have clear information. Basically, if we run this step 4 again, and we will do exactly that, we will see that for Alice and Bob will see that there was some noise in quantum communication. It might mean that, for example, our channel is not perfect, which practically this is the case. But it also might imply that somebody tried to mingle with our quantum state. So how we will do it, we will have B matching indices as we had before. Alice kept A needs to be updated. And Bob is sorry, I froze for a moment. Not enough RAM. Bob guessed the code B matching indices, and now we can see exactly what was actually kept. Because yeah. Okay, as you can see, they are off by 1 bit, and that is very, very interesting. That they are off by well, technically by 2 bits, right? I need to format it better so we can see it easily. Yeah, now they are off by 3 bits, which is even more scary. So yeah, what does it make our protocol completely pointless? So that's a very good and very important question. No, that is not the case. we will have yet another step. And what we will need to do is actually, for the example to progress, is to ensure that there is a reasonable amount of the noise introduced. Because if there is too much noise, the protocol needs to be simply restarted. They start from scratch. But if there is enough noise introduced, then they can use the technique of information reconciliation and also the privacy amplification to fix those errors. Okay, so what we will do now, our kept strings already differ quite a bit, so that's very interesting. But what we will do is first generate the test indices, because right now Bob and Alice do not know which elements of their string match and which do not match. So what they will do is to more or less divide the string in half. So from our original 4n, here we have 2n, and then we will go to n. They will use the substring of n length for testing, and then actual remaining indices for the further key generation. And for the sake of our presentation, we will be really sure, we want to be really sure that test indices actually are of length we specify, so we want them to be of length exactly 4. So we generate our binary array, and we have our indices. So we will ensure that the length is of particular size. And what we will do also is we will set the seed, for example, to 100 for starters. Maybe something else. I would like here this string to be length for 8. This is on. It would work with other lengths, but it is easier for the presentation. So here we have 9. Okay, we have around 8. And look how much noise if introduced. We will see if actually it will work. Okay, so what now Alice will do is tell Bob, here are the test indices. So Alice test A, Alice, it will be based on the kept A, so only the qubits that were measured in the same base. We will use test indices, and Bob test A, Bob kept A, test indices. And let's say that we will only want to we will allow only for 1 qubit being off in the test indices. If we see that there are 2 qubits off, we will simply say, hey, this is too much noise, we need to restart the protocol. There was so much interference that we are not sure, we do not have any we do not have strong enough guarantees on the procedure anymore. So we will set our threshold to 1. We will count our not matching elements. Yeah, so we will compare the test strings and then count how many of those are true. If not matching element is greater than threshold, we'll print restart the protocol. Otherwise, we can continue. Let's see how it works. Okay, that's good. So test indices were 1, 2, 5, and 6. So only one element was not matching. That's cool. Okay, so now let's see with what strings we are left. That's very important for us. So we will have final indices. So those are the test indices that we used before, but a few lines above we compared to 1. So the remaining one are can be retrieved by comparing to 0. So Alice final A is Alice kept A with final indices, and Bob final A is Bob kept A with final indices. That's good. Of course, it can be undefined because we do it in the while loop, but it is defined. So first of all, let's see what are the strings. Okay, those are mismatching by 1 bit. That's good. We have some noise. So right now, we will use the idea of information reconciliation. This is the idea of error code correction, and it is done over a public channel. So any data required to correct the errors is sent over public channel. So this is a very, very big brain topic. Let me use the lens. Error code correction is super big brain topic, and in the future probably we will dive very deeply into it. But right now we are at our regular brain size. We're just trying to get some fluency with the Qskit library and the general ideas and have some fun along the way. So we will not dive very deeply into error code correction, although it is very important topic. So we will look into it further. And for us, what is important right now is the idea of the linear code. Code is the linear coding have this very interesting property that if we encode message that consists of A and B, it is the same as encoding N and then encoding B. Okay, this is like linear algebra 101, right? This is simple linear transformation. It does not matter if we perform the coding on the sum or on the parts. And one of those codes is called Humming 7.4, and it's very interesting code. I have more about it in the notebook that is in the description. But now we will use false coding just for the sake of readability and brevity. Okay, so with this simple idea, we can actually come up with very interesting scheme for ensuring that we fix the noise. So our Bob final A, we can think about it as Alice final A plus some noise, right? They differ. The noise would be the introduced here, and because they differ by one on the position one. Okay, so if Alice would send an encoded message to encode Alice final A to Bob, then what he could do is to do the following: encode his message, which is equal to some noise. Then, by using this linear property, and with that, if he encode the Bob final A and subtract the encoded he will have encoded some noise. Then it will be enough for him to decode the noise, and from that he will retrieve Alice final A. And that is super powerful property. As I said before, for more details, go into the notebook. We will not implement it in here. It takes quite a lot of time, and there's a lot of additional theory for make it actually not a lot, but reasonable amount of additional theory. But this way, Bob can easily retrieve the Alice final A, and because the noise for Eve will be different, then it will not work as well with her. And what is more important, the linear code can be represented as a matrices, and this means that Alice can always select a different matrix every time, which makes it very fun. After that, they can use the so-called two universal hashing to ensure that the created key is as safe as they need. But for us, for this screencast, what was important is the part about if always introducing noise if she's interfering. This is due to the so-called no cloning theorem. So thank you very much for your time today. Remember to like, subscribe, share with a friend, and leave a comment on what I could do better. So yeah, next time be prepared for a surprise.